Most candidates score 5 out of 10 on this system design question. Today, I will show you exactly how to score an 8 or above on the URL shortener design. Every phase earns you XP, and by the end, you will know more than 85% of candidates walking into this interview. Here's the prompt straight from a real interview. Design a URL shortening service like bit.ly. Users enter a long URL, get a short one, click the short URL, get redirected to the original. Optionally, track analytics on link clicks. Expected scale 100 million URLs created per month. Sounds simple, right? Here is the thing 80% of candidates jump straight to the database. That is a mistake. It costs you 2 points before you have even started. Smart candidates start with API design. Before drawing a single architecture diagram, define your API contract. This shows the interviewer you think like a senior engineer. First endpoint, post to API v1 URLs. The client sends a JSON body with a long URL and an optional custom alias and expiration time. The server responds with the generated shortcode, the full short URL, and a creation timestamp. Second, get shortcode. This is the redirect endpoint. No request body needed. The server looks up the shortcode and returns a 302 redirect to the original URL. Third, delete API v1 URL shortcode for URL owners to deactivate their links. Returns a 204 no content on success. And fourth, get APv1 URL shortcode stats. Returns click count, creation date, and last access timestamp. Pro tip. Defining your APIs first gives the interviewer a clear contract to reference throughout the discussion. It also reveals your read-write patterns before you even touch the architecture. Phase 2 requirements. Before you draw a single box, nail these questions. First, read-to-write ratio. URL shorteners are read heavy. For every URL created, it gets clicked maybe 100 times. So we are looking at a 100-to-1 read-to-write ratio. This fundamentally shapes our architecture. Second, do URLs expire? This changes your storage strategy entirely. Let us say no default expiry, but users can set a custom TTL. This means we need a TTL field and a background cleanup job. Third, the math. 100 million URLs per month, that is about 40 writes per second. At 100-to-1, that is 4,000 reads per second. In a year, 1.2 billion URLs, roughly 600 gigabytes of storage, very manageable. Fourth, short code format. We need codes that look random but are collision free. 7 characters using base 62, that is letters and digits, gives us 3.5 trillion unique combinations. More than enough. 4 requirements clarified before touching architecture. Most candidates cover 0 or 1. This alone puts you in the top 30%. Phase 3, high-level architecture. Now we draw boxes, smart boxes, where every component is justified, starting with the client. Users send post requests to create short URLs and get requests for redirects. Next, a load balancer. With 4,000 reads per second, we need horizontal distribution. Round robin or least connections either works here. Behind the load balancer, stateless application servers, URL creation and redirection logic lives here. Any server can handle any request. That is what makes horizontal scaling possible. Now the critical decision, where do you store URL mappings? We need fast key value lookups, a simple data model, and horizontal scalability. This screams no SQL. We will go with DynamoDB, and I will explain exactly why in the cap theorem section. Finally, a caching layer. Redis sits between your app servers and the database. The top 20% of URLs get 80% of the traffic, classic Pareto distribution. Cache those hot URLs and you handle 80% of redirects without ever touching the database. 5 components, every single one justified. Let us define the schema. Our primary table is URLs. The partition key is shortcode, a 7-character string, then long URL up to 2048 characters. User ID with a global secondary index so we can query URLs by user. Created at timestamp, expires at as a nullable timestamp for optional TTL, and click count as an atomic counter. Why shortcode as the partition key? Because every redirect is a simple key value lookup. Shortcode maps to long URL. And since shortcodes are random, they distribute uniformly across partitions, no hotspots. For analytics, a separate URL analytics table, composite key, shortcode plus timestamp. Each row stores IP address, user agent, referrer, and country. The write path is straightforward. Grab a pre-generated code, write to the URLs table, return the short URL. The read path, check Redis cache first. On a cache miss, query the URLs table, log the click to analytics asynchronously, and return a 302 redirect. Now let us talk cap theorem. This is where your database choice gets properly justified. Cap says in a distributed system, when a network partition happens, you can only guarantee 2 out of 3 properties. consistency, availability, and partition tolerance. For a URL shortener, we choose AP, availability, and partition tolerance. Here is why. Availability is critical. A redirect service that is down means broken links everywhere. Users get 404 errors, shared links die across the internet. That is unacceptable for any production system. Partition tolerance is non-negotiable. Network partitions will happen at scale, and your system must keep serving redirects regardless. And consistency? Eventual consistency is perfectly fine. If a brand new URL takes 100 milliseconds to propagate to all replicas, nobody notices. URLs are write once, read many. So why DynamoDB specifically over the alternatives? PostgreSQL is a CP system. It sacrifices availability, has vertical scaling limits, and sharding is complex. Cassandra is a great fit. It is AP with linear horizontal scaling, but it requires significant operational expertise. DynamoDB is AP, gives single-digit millisecond reads, is fully managed with zero ops overhead, auto scales to any throughput, and the partition key maps perfectly to our short code. Phase 4, Deep Dive. How do you actually generate the short code? This is what separates a 6 from an 8. Approach 1, Random Generation. Generate a random 7-character base, 62 string, 3.5 trillion possible combinations. Sounds great, but at high throughput, two servers could generate the same code at the same millisecond. That is a race condition, and it means you need a read before write check, adding latency and complexity. Approach 2, Key generation service. This is the one that scores points. A dedicated service pre-generates batches of unique codes and stores them in a pool. When an app server needs a code, it grabs one from the pool. No collision possible, no race condition, no read before write check needed. But what if the KGS goes down? You run two instances. One generates from the odd range, the other from the even range. They never overlap. No single point of failure. Each server grabs a batch of 1,000 codes into local memory and hands them out. When the local batch runs low, it fetches more from the pool. Simple, elegant, bulletproof. Scalability. This separates a 7 from a 9. Three strategies you absolutely must mention. First, CDN at the edge. Short URL redirects can be cached and served from CDN nodes closest to the user. The request never even hits your origin servers. Massive latency reduction and cost savings. Second, read replicas. Writes go to the primary database. Reads spread across multiple replicas. At our 100-to-1 read-write ratio, this is critical. Third, 301 versus 302 redirects. This is a trade-off question interviewers love. 301 is permanent. The browser caches it, so repeat clicks never hit your server. Great for performance, terrible for analytics because you lose visibility on repeat visits. 302 is temporary. Every single click goes through your server, so you can track everything. If analytics matter, and for most URL shorteners they do, go with 302. Let us see how we scored. Requirements gathering 9 out of 10, API design 8.5, high-level architecture 8.5, deep dive and key generation 8, scalability and trade-offs 8, overall 8.4 out of 10. That puts you in the top 15% of candidates. The average score on this question is 5.2. You just scored 3 points higher by following a structured approach. If this breakdown helped you see system design differently, smash that like button and share it with someone prepping for interviews. It genuinely helps the channel grow, and if you want to take it further, Interview Forge lets you practice this exact question with an AI interviewer that scores you in real time. 3 free sessions every day, no sign-up wall. Head to interviewforge.tv, link is in the description. Next video, we are tackling real-time chat system design. Hit subscribe so it lands in your feed. Drop your score in the comments. I want to see who beats 8.4.